This video is to take you through Kirchhoff's voltage and current laws to show how voltage and current are divided across the circuit. Just full disclosure, I'm recording this without my mouse and stuff, so hopefully I'll be able to manipulate the keyboard okay. Just for a little bit of background into what we're going to be looking at on the breadboard. If you have something called a series circuit, this might be your voltage source. So this would be like your battery, and the symbol for the battery is a bunch of lines, like you alternate like a long line and a short line, and the longer line represents the positive terminal of the battery and the shorter line represents the negative terminal. And then you might connect things in your circuits like resistors, and the symbol for a resistor is a zigzag line, just like that. And a resistor could be an actual physical resistor, which we'll look at in Tinkercad, or it could represent something like an appliance that you have plugged into your circuit. It could be anything that creates resistance. When you have a series circuit, the resistors are connected one right after the other, and the key idea is that they're in the same loop. So if I turn on the laser pointer, so they're in the same wire, and there's no division in the wire. So the current, the way engineers think about the current would come out of the positive terminal of the battery, and it's going to flow through each of these resistors and then come back into the negative. That's not a great scientific way of putting it, but it's an okay way to think about it. And the battery has a certain voltage. So the other day I actually bought a 9-volt battery for smoke detectors, but the battery can be whatever the battery is, your power supply, and it has a certain amount of voltage. And in Kirchhoff's voltage divider, what happens is like you lose a certain amount of voltage as you go over each resistor. Kind of think of it as like the top of the battery is like a waterfall, and the water's going to run downhill, and it's going to go over one waterfall and then over another waterfall and then another one, and eventually it's going to go back to the bottom. And all of the voltage drops, like how much voltage it loses over each resistor, has to add up to the total amount of voltage in the battery. Now that's opposed to something called a parallel circuit, where the resistors are connected in parallel. So there's my battery. That's a terrible battery, but and so it might look something like this. Now this is really exaggerating the parallelness of it. So visually, the resistors can be in different locations because all the line represents is a wire, but I won't get into that here. And in this kind of circuit, if you look at the top here, this is all just one wire. Okay, it's like a wire coming out of the top of the battery. And down here at the bottom is another wire. It just comes out of the bottom of the battery. And so if you were to measure the voltage over the battery here, it would be the same as if you measured it here or down here. In other words, the voltage drop over every resistor is going to be exactly the same as the voltage over each battery, or over the battery. But what's different from the series circuit is that the branches of the wires actually divide. So when your current's coming out, and then it hits this juncture, and some of the current's going to go through this first resistor, and some of it's going to keep going. And then the same thing will happen here. And so what happens here is that you actually divide the current, where the voltage stays the same. So in a series circuit, the voltage over each resistor is different, and it will add up to the total voltage of the battery, but the current going through each resistor is exactly the same. In a parallel circuit, the voltage is the same because each resistor is connected directly to the battery. That's called my cat. But the current will be different. And if you were to add up the current going through this resistor, and this resistor, it would be equal to the total amount of current in the circuit as a whole. Scram. Okay, so that being said, what we're going to do is take you over to Tinkercad, I hope. So we're going to exit out of there. Sure, we'll save that. Why not? Okay. and I should have Tinkercad up and ready to go. So what we've got here is a breadboard. In electrical engineering, a breadboard is the way that you prototype a circuit. So a permanent circuit, the kind that you would see inside an electrical device, is what's called like a printed circuit board. And it's once you're totally sure that this is the circuit that you want, you actually like print it onto a board and it can't be changed. But you obviously don't want to do that to get started. And so what you do in a lot of engineering classrooms is you use something called a breadboard. And hopefully you can see my mouse okay. One thing I like about Tinkercad's breadboards is if you hover over the different holes, it tells you what's connected to what. So right here at the top, you'll see that there's a band and it's like negative, it's like labeled negative. And when I highlight over that, all of the holes like are highlighted green, it means that's basically one wire. Everything that's plugged into that row is going to be connected to each other. So if you wanted to ground something to your ground your power supply, you want to ground a resistor or complete your circuit by grounding it, like you can just go anywhere there. And then the next row down is positive. And then you'll see something similar down at the other end. So you've got like this power and ground, and they run, in this case, horizontally. Now, in between, you'll notice that the columns here are connected differently. They're not connected horizontally, they're connected vertically. And so anything plugged into, like, I guess that's row 26, would be connected to each other. So if you have two components and you want to connect them, you could plug one in here and then one in down here, and they would be connected. And then you'll notice that they're not connected over this gap. And that is for if you were using an IC chip of some sort, which is what we get into in our digital electronics. I'll just like pull one up, like an AND gate. These are these chips, and you can pull them out, and you'll notice that they're designed to fit perfectly over that gap, and that way you're not tying the pins of the chip to each other, because that would short circuit the chip, and they get really hot, and they'll, it's bad. So that was a NAND gate, I guess I pulled off of there. So what we're going to do here is build a series circuit and a parallel circuit, and then I'm going to hook up the multimeter to it so that you can observe, at least digitally, how these laws work, as opposed to just like a teacher telling you that this is how it works. So, and bear with me, hopefully this will go smoothly. So to connect a wire in Tinkercad, you can just click anywhere and pull the wire, and you can drag it out. If I click, I can create a bend in the wire. So if I don't want the wire to go like right over the top of my breadboard, I can bend it. And then typically, like positive, you want the wire to be red. It just helps you remember, okay, that's positive. And then I'm going to come here and grab my negative, and I'm going to come over here, and we'll just put that right there. And then usually you want your negative or your ground to be black. Now, what that did was that means that everywhere in this row here is going to be tied to power, and everywhere in that top row there is going to be tied to ground. So I'm going to build a really simple series circuit using my resistors, and these resistors, I set them for 1 kilo ohm, 2 kilo ohms, and 3 kilo ohms. So I set that up in advance, so I wouldn't have to do that. You can change that just by clicking on it. So this one is the kilo ohms. You might notice that there's different colored stripes on them, and that corresponds to the value of the resistor. So to build this circuit, I'm going to take my resistor and I'm going to plug one of it in to this power rail, okay? And then the current's going to go out of my power supply, and it's going to go into the resistor, and it's going to dump out in this column, anywhere in this column. And I'm going to take my second resistor, and I actually want to turn that. There we go. And I'm going to plug one end of it into that same column here. So this end of this resistor is connected to that end of that resistor because of where they are in the breadboard. And then I'm going to take this one, and we're going to plug that into, oh, I got to go over one, into the ground. Okay. So this is a series circuit. I put like one resistor right after the other, and just so you can trace where the current goes. So it's coming out, it goes into this power rail, then it's going to hit this resistor, then it's going to flow into this resistor, and then remember the columns are connected. So then it's going to come up, go through this resistor, and then back to ground here, and then technically back to the power supply. All right. Okay. So there's that. So I'm going to go ahead and start the simulation. I have this set for 500 volts, which is actually kind of like a ridiculous voltage to set it at. But because I made the resistances so high, I wanted, if Mr. Rollins decides to work the numbers out, I wanted you to get something more than like microamps or something for your current. Anyway, and it tells me that there are 83.3 milliamps running through that. That comes from Ohm's law. So if you do V equals IR, voltage equals current times resistance, you would add up all these resistances. They would add up to 6,000 ohms. And then you do 500 equals current times 6,000. 500 divided by 6,000 is where the 83.3 comes from. I'll leave that for somebody else to cover. Now, this device right here is called a multimeter, and I have it set for voltage. So I'm going to have to stop the simulation, and what I'm going to do is measure the voltage at several different places. So we know that the voltage coming out of the power supply is 500 volts. The first place I'm going to measure the voltage is going to be over the first resistor. And I might have that backwards. That was like the negative end. All right, so put that there, and then we'll put that right there, and that's my positive one, so we'll make that red. Sorry about the crisscrossing. I have actually awful circuit design aesthetics. All my circuits are usually a mess. They work, but they're a mess. All right, so if you notice where I put this, remember that where this resistor is, it's connected to everything in that row there. So by putting the wire here, it's the same as putting it at the end of the resistor. And then I put it, that is the same cat, and now he wants to come back in, and I'm not giving it to him. So I put the negative terminal right here, and what we're going to do is measure the voltage over that resistor. So you'll notice that even though there's 500 volts coming out of the power supply, when I measure the voltage over that resistor, I'm only getting 250 volts. So that's half of it. Now, if you remember, I said I set this for like 1 kilo ohm, 2 kilo ohms, and 3 kilo ohms. So you might be thinking, well, 3 kilo ohms is like half of the total. Like if you add the other two up, yes. And it is like a linear relationship, so it's going to be proportional there. All right. Now I don't think I can move. Yeah, I can't move my wires without stopping the simulation. So like just notice that, maybe write it down on a piece of paper. Like, okay, the first one was 250. Now what I'm going to do is take this wire and move it, and I'm going to move it over to the second resistor. You can crisscross them if you want, but it'll make your voltage negative. That's an activity that we did in digital electronics. So now I've got this over the second resistor here. Remember, if I put this wire here, it's connecting it to that end of the resistor, and then over here because that whole column is connected. And we're going to measure the voltage there, and that is 167 volts. So the first one had a voltage drop of 250. The second one has a voltage drop of 167. And then let's do the last one. So I'm going to go ahead and move this and move, whoops, don't want to move that. There we go. Okay, and now I've got my leads over the last, actually, no, I don't, just kidding. I got to move it over. I didn't quite have it lined up. I need it one more over. There we go. So now it's measuring it over the last resistor, and the voltage drop is 83.3. And if I add all of those voltages up, I'm actually doing it 11 plus 9 is 2. I get 500.3. So you might be wondering, well, that's not exactly the 500. That's because real life is not as perfect as Math World. So you've got like Math World, and then you've got like actual stuff. Yeah, and even though this is a simulation, it's still going to take into consideration stuff like resistances of the wires, which normally we don't take into consideration unless you have some kind of massive amount of wire. So the point there is that the voltage drops over each of the individual resistors will add up to the total amount of voltage. And I think that's probably all like we need. Yeah, and you can analyze the circuits in a lot more detail, but that's something that you'd probably want to cover like in class. All right, now what do I want to do? Over on this side of the board, then we're going to build another circuit over here. Let me just move these out of the way just to clean it up. I probably could have been more efficient at doing this, but oh look, I put a little wire in there. Whoops. You know what? Yeah, I quit. Okay, and we'll just delete these wires for the moment because I'm probably going to move my multimeter. So these are the same 3 resistors over here. This time though, I'm going to connect them in parallel, and I think I'm going to use a couple of other wires to do that. So I still have my power and ground, so that's fine. I'm going to take a wire and I'm going to run it. Yeah, I don't know where I want it to go. I guess we'll run it right there. Oh, let's make it blue for fun. And then, so that's going to be connected to power. So let's, and what that's going to do is put power in that entire strip. So basically I just connected that power rail. All right, so let's go get these resistors in there. So I'm going to turn my resistors around. Go me. All right, and let's put one resistor there. And oh, come on. This would go smoother if I had a mouse, I promise. Although those of you that know me know that that's probably not true. I'm so sorry. Like, I have a cat that just sounds like he's not doing well. He's fine. All right. So what we've done here is we've connected these resistors up, and pretty much what we've done is we've tied all of them to power. Okay. And then I'm going to take the other end of this and we'll complete the circuit by tying it back to ground. So the reason I didn't necessarily just connect all the resistors straight to power and ground is that it's just a little bit uncomfortable and a little bit crowded. All right. So now if I were to measure the voltage drop, let's go ahead and we'll measure the voltage drop over any of these resistors. So I can put that down there. Let's make that black, and then we'll put this here and we'll make that red. If I were to start the simulation, it is going to show a voltage drop of 500, and it doesn't matter where you measure it in that circuit because like all of those resistors are connected directly to power and directly to ground. And even though in the circuit schematic diagram that you have, it looks a little bit different, like it's just a wire. So you can make your wire as long or as short as you want, or get rid of it altogether and just connect everything directly. So what we're going to do here, though, is measure the current. So notice that there actually is more current going through the circuit here. It's 917 milliamps. And that's because even though those resistors are all the same as the resistors before, when you connect them in parallel, they actually end up with a lower equivalent resistance, which is an awful formula and something that Mr. Rollins and I talked about today because I don't do the formula the way PLTW does because I think it's hideous. But you can figure out what the equivalent resistance is, and it's actually a much lower resistance, which increases the amount of current. So what we are interested in, I'm going to actually write that number down. So 917 milliamps. I'm going to go ahead and change this. So this was in voltage mode. I'm going to change it to amperage mode so that it is now going to measure current instead. And what we're going to do is measure the current through each resistor. So I think I can do this okay if I connect it, like normally I would say connect it not over the resistor, but I think we'll be okay. And there's just not enough space in the circuit board to insert the meter elsewhere. All right, so what I've done is I've connected it over the resistor. Now remember, this time we're measuring current, not voltage. And what you can see is that something went horribly wrong. Okay, that is, I guess I can't do that. Let me move this out of the way. Okay, I'm just gonna pause the video for a second because I want to figure out the best way to do this, and you don't need to hear me do it. Okay, all right, we're back. So you'll notice I rearranged this a little bit because in order to measure the current, measuring current is such a pain. You need to break open the circuit and put the meter into the circuit. And so I had to spread everything apart so that I would have room to break open the circuit. So you can see what's going on here, all right? So we got the rails are the same. This is my positive rail, and what I had to do is I had to run the current like over here, all right? Where it is going to get picked up by the multimeter right here. And it's going to go up and come through like that, and then measure the current going through that resistor. And then this is still connected to power, okay? So this is going to connect down here, and I just had to create more space to do it. And then, of course, these are going to be connected down here. I had a bridge over that little ravine, and then everything on this side here is going to be grounded. But what I needed to do is I needed to break open the circuit in order to put the multimeter in. There is minimal chance like you would ever need to do this to connect it up. So when I start the simulation, then you'll notice that the current through that first resistor is only 250 milliamps, even though the current going through the entire circuit is 917. So if you want to write that down. Now I'm debating whether or not I want to pause the video again, because what I need to do is I need to take the multimeter out of the circuit, put the circuit back together, and then break it open in another spot. And I'm not 100% confident that I'll do that correctly on the first try. I will mess something up. But let me go just move these out of here. So I'm just moving the wires out of here. So I've got to put this circuit, like this piece of it, back together again. So that this is going to run like straight through there. And now I have to insert the meter in the next branch of the circuit. So I think what I need to do is I need to run the positive wire to here to pick up that first resistor, and then the negative wire over here to pick up the second resistor. So I had to put this part of the circuit back together again. So if I follow this, the current's going to come out through here, and then it's going to have to kick on over, go through the meter, and then come back to the second resistor, which I'm still not sure. That is not where I want to put it either. Because of the other division thing. Crud. Okay, so we're back and we're better than ever, except that this is a mess. So I'm going to try to recap what I have done here in order to get this to show what I wanted. So I think I mentioned, although I can't remember 10 minutes ago, that when you put the meter in to measure the current, you've got to break open the circuit. And so in order to make sure that I'm breaking open the circuit in the right places, I had to spread out all over the board and connect all these wires. When I said that my circuit design aesthetic is terrible, I'm not kidding. It's really bad. But let me see if I can explain what I got going on here. Okay, and then we'll talk about Kirchhoff's law, and then we'll just put this lesson to bed. So here's what we have happening. So we have the power supply the same as before. It's 500 volts, and the resistors are 1, 2, and 3 kilo ohms. We've powered up this rail, okay? And then we're running the current way over here. Now, I probably didn't need to run it that far away, but I wanted to allow myself some space. Now, the current then needs to be able to go to all the resistors. And so if you look at like how this is connected, like it's connected down here to like the second one down here, and then we're bridging over to connect it to the third one. What makes it hard to follow is I've had to put the meters into the circuit. So you're not just seeing the wires connecting the things, like it's like detouring over to the meters, and instead of using 1 meter and moving the wires around, I put 3 meters on there so we could see them all at once, and I could build this whole thing. So going through the first resistor, the current's going to come here, and then it's going to branch into the first resistor, and right in here where my mouse is, that's where I've put that first multimeter, which is giving us the 250 milliamps, which I think is the same as what we had before. Okay, so that's the current going through the first resistor. Then if we follow, and then it comes out of the resistor, and then this whole part is unchanged. It still goes back to ground. Then the next part of this comes down to the second resistor, and I had to branch that off, because what I was doing when I had the video paused is I was like putting it into the second branch, but I was inadvertently measuring the current through the second and third resistor, and I only wanted the second resistor. So I had to make sure that I was branching off the current, and none of that probably means anything to you. So because you've never studied it before. But anyway, we moved this down, and then right here is where I inserted the second meter. So the current's going to now go up through here. We're going to measure what the current is, and then it's going to come through this resistor and back to ground. And then the last piece, we had a bridge power. And then because this is the last resistor in the circuit, I was able to put the multimeter in right here. So the current goes up here, through here, and then through the third resistor, and then back here. And you'll notice that I had to stagger these resistors in order to insert the multimeters in. Okay, now that is probably like, if you're wondering, well, why aren't we going to breadboard this ourselves? Now you know why. Like, this could take like multi-class periods to get it right. But what I did want you to see is that if you add up the current through the first resistor, second resistor, and third resistor, it will add up to the total amount of current in the circuit. Okay, so all of that just to show you that if you add up the current through the three resistors, it will give you the total amount of current. So if I can come back, you guys don't care about that. We want this one. There we go. So what I just showed you was like that if you have the current going through this circuit here, if you add up the current going through each branch, it will give you the total amount of current going through the entire circuit. The voltage is much, much easier to show, which is now readily apparent that if you add up the voltage drops over each resistor, it will add up to the total voltage in the battery. Current is much more difficult. And just in case you're probably not wondering, but what I needed to do that was so tricky is like I was putting the meter here, like here and here, and you can't put them there because of the fact that it's before the break in the circuit. Like you've got to break open the circuit and like put the meter in right there and right there in order to measure it. And that's what took so long. I had to like move the wires around and make sure I was putting the multimeter in the right spot. So my apologies for how that got bumpy at the end. Hopefully it did help you get a little idea of how a breadboard works, how it does simulate it, and it verifies for you what these relationships are between current, voltage, and resistance.